Greeting everyone, and I'm going to present my project and presentation with a title like Emitting diode, which we can simplify as LED. There are 3 journals had been selected for my project and presentation. The first journal is Perovskite light emitting diode with external quantum efficiency 22% via small molecule passivation. And the second selected journal is efficient and bright white light emitting diode based on single layer heterophase halide perovskite. And my third selected journal is improved performance of flexible perovskite light emitting diode with modified P.PSS whole transport layer. The first journal to be discussed with a title Perovskite light emitting diode with external quantum efficiency 22% via small molecule passivation. Executive summary for Journal 1. The defect passivation strategy by employing a novel organic passivation agent, which is ethoxylate trimethylopropene triacrylate, which we can simplify as ETPTA, with a chemical bond C and O functional group to interdiffusion passivation effect on improving perovskite LEDs device performance. A COSI2D P2PBBr4, CSPBBr3, and perovskite precursor solution was prepared, and COSI2D perovskite layer were manufactured by one-step solution spin coating method, and EA with ETPTA as anti-Showan solution was dropped during this process. The modified P.PSS solution was spin coated onto ITO, which is indium tin oxide substrate, and transferred into nitrogen filled gearbox. Precursor perovskite solution was spin coated onto the modified P.PSS, which we can simplify as MP.PSS substrate. The TPBR layer and LIF/AR electrode were deposited using thermal evaporation system. Research methodology for Journal 1. This is a flowchart of research activity for ETPTA to PE-LEDs. PE-LED actually is a perovskite LEDs. The ETPTA with the solution were purchased with a mixture on modified P.PSS and preparation COSI2D perovskite, and this is a precursor solution, which will be go to indium tin oxide coated glass substrate, which is green by sonation in detergent, deionized water, acetone, isopropyl alcohol, dry by N2. After that, we'll go to UV ozone treatment for ITA for 10 minutes. Then we'll go to the MP.PSS spin coated onto ITO substrate with 9000 RPM for 60 seconds and baked with a temperature 160 degrees for 50 minutes. The substrate will transfer into nitrogen filled gearbox. The precursor perovskite solution spin coated onto MP.PSS with 2000 RPM for 2 minutes. After that, we'll go to a spin coating for 40 seconds. Then 100 microliter ETA or ETPTA pour onto the film for perovskite crystallization, and followed by annealing at a temperature of 80 degrees for 20 minutes. Then we'll go to a thermal evaporation system with a shadow mask under high vacuum with 1 times 10 power minus 4 Pascal and deposited with a TP layer with a 60 nanometer and LIF slash Hale electrodes with a ratio 1 nanometer slash 100 nanometer. And the final process will go to a film and device characterization measurement. This is a figure 1. We show a ETPDA on perovskite. This is a layer with ETPDA, which is an interface and sandwiches between perovskite layer and TPBI layer. Result and discussion for Journal 1. Figure 2 is a steady state photoluminescence, which we can simplify as a PR. The emission peak of the pristine perovskite film was located around 512 nanometer, which is shown in the red line as shown with the pointer. The PR peak of the perovskite film with ETPDA treated located at 509 nanometer, which was slightly blue shifted. So this is the blue line, which is with ETPDA treated, which is a slight shifted compared with the red line. It could be attributed to eliminate the corresponding trap state present on the perovskite layer and reduce undesired non-relative combination. The figure 3, the emission image of perovskite film with and without ETPDA treatment under ultraviolet excitation with 365 nanometer. The PL intensity increased by about 2 times when ETPDA was introduced onto perovskite film. As we can see from this figure 3, this object with ETPDA treated, which will be brighter, and the PL intensity actually is a 2 times compared with object which is without ETPDA treated. Figure 4. For PL average lifetime, the PL average lifetime of the cosi-2D perovskite film will increase from 6.30 to 7.04 nanosecond after the ETPDA treatment. This is confirming the reduced possibility of defect-induced recombination. That we can see, this is the red line, which is without ETPDA, and compared with a blue line, which is treated with ETPDA, and the PL average lifetime will be longer. For figure 5, PLQY, which is the photoluminescence quantum use of the perovskite film. The PLQY of the perovskite film with the ETPDA additive reached up as high as 90.02% compared to that film without additive, which is 60.93%. We can see from this graph with a red line, which is without ETPDA, which is lower compared with ETPDA, which is in the blue line, which is higher, compared with without ETPDA. The photoluminescence quantum use improvement was primarily due to suppressed non-radiative processes by the ETPDA interdiffusion, and the result unveiled the defect precipitation function of the ETPDA treatment. For figure 6, which is a SAM image of perovskite film with and without ETPDA treated, the perovskite show more denser film without pinholes compared to the thin film without ETPDA treatment. In here we can see this is a object with ETPTA, the perovskite film with ETPTA, and the upper image show is the perovskite film without ETPTA, which have a pinhole which in blue dot in black dot, but with perovskite with ETPTA that will be out pinholes and more dense, as we can compare with these two images. It's indicated that the small organic molecule could penetrate into the perovskite film along the grain boundary to reframe pinhole during the anti-solvent process, and resulting in reducing non-radiative recombination due to leakage current. For figure 7, the Fourier transform infrared, which we can simplify as FTIR. This is a figure 7 FTIR spectra. The upper image graph, we can see with 4 different lines, with the black with a ETPTA, which will be lower, and with a in brown color, which is a PBBR2, and the blue line is PBBR2 with ETPTA. This is blue line, and this is a brown line, and the green line shows a perovskite with ETPTA. So, and we can see deeper for this one. We go deep for this area, we can zoom in. So this is a, in the black line is a ETPTA, and the blue line is a PBBR2 with ETPTA, and the last one with the green line is perovskite with ETPTA. The FTIR spectra for PBBR2 ETPTA, PBBR2 with ETPTA, and perovskite with ETPTA film is being coated on a silicon substrate. The stretching variation of PBBR2 at around 1635 centimeter -1 shifted to lower wave number 130 centimeter -1 in PBBR2 with ETPTA mixture film. So that means here you can see this one, the variation for PBBR2, which is in brown color, and shifted to the PBBR2 with ETPTA, which is a blue line here. So they shifted. It indicates that the chemical bond of the PBBR2 is weakened with the addition of ETPTA. A clear shift in the chemical bond C and O characteristic peak of ETPTA was observed in the spectra of the PBBR2 with ETPTA mixed film and perovskite film with ETPTA treatment. It confirmed that ETPTA was interacting with a non-coordination PBBR2 in perovskite film. Figure 8, external contour efficiency, that also we can simplify as a EQE, current density curve of LED. So this is a graph, figure 8, to show the EQE current density curve of LED. The peak EQE with ETPTA treatment reached 22.49% at 0.13 milliamp per centimeter square, with luminance of 77 candela per centimeter square. As we can see here, this is the blue line. The maximum we can reach for the EQE is 22.49%. And this is representing a record for the green perovskite LEDs. This demonstrated that the VTPD treatment provided a good channel for effective recombination of electron and holes. EQE for perovskite LEDs without ETPDA treated exhibited lower EQE of 16.79% at 0.8 mA per centimeter square. Journal 2. Efficient and bright white light emitting diodes based on single layer heterophase halide perovskite. Executive for Journal 2. Calcium lead iodide, which is a CSPB-I3 single emissive layer with both alpha and delta phases, can act as a unique emitter with both efficient injection and recombination of carrier for perovskite white LEDs, which we can simplify as a PEW LEDs. Synergetic effect at the alpha stroke delta heterophase interface realize charge injection balance in the two phases and endorse the PEW LEDs with highly efficient and brightness. Synthesis of CSPB-I3 quantum dots, we can simplify as QDs were prepared and P dots PSS solution were spin coated on the ITO coated substrate. TFV and Q quantum dots were deposited layer by spin coating and bake. TPI and LIF stroke AL electrodes were deposited using thermal evaporation system. CPD were taken along the alpha dash calcium lead iodide to delta calcium lead iodide phase. Research methodology for Journal 2. This is a flowchart to show research activity for white LED based on single layer heterophase halide perovskite. Synthesis of calcium lead iodide quantum dots preparation, and we go to a P dot PSS solution spin coated onto indium tin oxide, which is the ITO coated glass substrate, with a 4000 rpm for 60 seconds and baked at a temperature with a 140 degrees Celsius for 15 minutes. And TFV and quantum dot deposited layer by layer with a 2000 rpm for 60 seconds, baked at 130 degrees Celsius for 15 minutes, and temperature with a 120 degrees Celsius in ambient air for 30 minutes with a 60% of humidity. And the important thing is the humidity level plays a vital role in controlling the transition from alpha calcium lead iodide to delta calcium lead iodide. Then subsequently we go to the process with thermal evaporation system. We shadow the mass under high vacuum with 2 times power -4 Pascal, and we deposited the TPI layer with a 40 nanometer and LIF stroke AL electrodes with a ratio 100 nanometer stroke 100 nanometer to 100 nanometer. After that, we'll go through a characterization and divide measurement. The figure 9 is a PEW LED structure in which alpha with delta heterophase synergistic effect. Here we can see TPI BI layer and TFP, and this is a calcium lead iodide. In the red object we can represent as a alpha calcium lead iodide, and the yellow we can represent as a delta calcium lead iodide. Result and discussion for Journal 2. For figure 10 white LED, this is a figure 10 we show with a white LED. The photograph of the perovskite white LED device driven at 5.2 volts and featured a bright and uniform white emission. Figure 11 with the external control efficiency EQE and current density of the white LEDs with a high brightness with a luminance of 12,200 candela per meter square with a high efficiency of EQE 6.5% due to synergistic effect at the alpha to delta heterophase interface and down to the perovskite white LEDs. The efficient white electroluminance we can simplify as a EL originates from the superior charge injection into the alpha phase, alpha to delta change transfer, and alpha with delta valence relative recombination. So we can see here for the EQE for this line with the black line, the maximum we can reach is a 6.5%. For figure 12, scan photoluminescence with a PL and contact potential difference we can simplify as a CPD signal along the line. Okay, figure 12A shows the 2D control core PL mapping of typical area containing alpha and delta phase area. So this is the figure 12A, and this is a line for the CPD for this blue line, and this is the PL. FMSKPM frequency modulation scanning Kelvin probe microscope measures CPD corresponding to local surface potential in the same area in figure 12B. A strong correlation between the phase distribution and surface potential. The bright alpha calcium lead iodide area exhibit more positive CPD with an approximate negative 0.15 volt, whereas the delta calcium lead iodide area exhibit more negative with CPD with approximate about negative 0.25 volt. And this is the bright area which represent with the alpha calcium lead iodide, and the dark area is a delta delta calcium lead iodide. This result indicates delta calcium lead iodide phase experience more negative function which compared to alpha calcium lead iodide. The potential difference of alpha to delta calcium lead iodide provide an interfacial potential field to access charge injection from the alpha phase to the delta phase to improve the efficiency of the electricity driven white emission. Journal 3. Improved performance of flexible perovskite light emitting diodes with a modified P.PSS whole transport layer. Executive for Journal. Improved performance of flexible perovskite light emitting diodes PE LEDs onto ITO, which is a indium tin oxide coated PET substrate by using modified P.PSS as a whole transport layer. We can simplify as HDL. Solvent and dopant modification of the P.PSS solution will carry out by adding isopropyl alcohol, which is IPA, and PSS Na respectively to the pristine P.PSS solution. Both solvent modification P.PSS SM, which is a P.PSS plus IPA, and dopant modification P.PSS DM, which is a P.PSS plus PSS Na. We exhibited a significant enhancement in both luminance and efficiency. The modified P.PSS layer on perovskite film show a uniformly covered surface morphology without any defects and increased photoluminescence PR. Research methodology for journal tree. And this is a flowchart of research activity for improved P-latch with a modified P.PSS whole transport layer. P.PSS HDR preparation. We can go to the three different preparation, which is a P.PSS-PR, which is a P.PSS layer cast from a pristine P.PSS solution, and the second is a P.PSS-SM, which is the P.PS plus IPA, and the third preparation is P.PSS-DM, which is a P.PSS plus PSS-NA. The P.PSS solution spin cast onto a flexible indium tin oxide IT or substrate mounted on a glass plate and anneal at 150 degrees Celsius for 15 minutes. P.PSS control with a 50 nanometer. Perovskite precursor solution for COSY 2D was prepared, and we go to a spin coat onto a P.PSS layer with a 6000 rpm for 1 minute in a nitrogen filled glove box with a chlorobenzene CB drop onto a precursor layer after spin delay 20 seconds and anneal at a temperature 90 degrees for 1 hour. After that, we go to thermal evaporation under 10,000 power minus 7 torque with a 40 nanometer thick TPBI layer for hole blocking and transport electron, LF over AL electrons with a 1 nanometer / 100 nanometer bilayer cathode were deposited on perovskite layer. Characterization and device measurement. Result and discussion for journal 3. The figure 14 luminance versus voltage. The maximum luminance Lmax elevated from 1290 with a P.PSS-PR to 1850 for P.PSS-SM and 3940 for P.PSS-DM. So we can see from this graph, the blue line represented by P.PSS-DM and the black line represented by P.PSS-PR, and the red line represented by P.PSS-SM, which is a solvent modification, and the blue line is a dopant modification, and the black line is a pristine perovskite film. For figure 15, external quantum efficiency EQE. The maximum EQE increased from 6.64 candela per ampere and 1.57% for P.PSS-PR to 12.42 candela per ampere and 2.96% for P.PSS-SM, which is with a solvent modification, to 25.13 candela per ampere and 5.91% for P.PSS-DM, which is a dopant modification. And this is the blue line, which is a P.PSS plus PSS-NA, which is a P.PSS-DM, which is a dopant modification. From red line, which is a P.PSS with IPA, and this is a P.PSS-SM, which is a solvent modification. For black line is a P dot PSS with pristine, which is a pristine perovskite film. So as we can see here, the P dot PSS DM, which is a dopant modification, is having a higher EQE compared to P dot PSS SM and P dot PSS PR. Figure 16, current versus voltage. Current density increase after the solvent modification of P dot PSS solution, and the dopant modification further increase to the current density. Improved device performance can be attributed to the enhanced hole injection achieved by lowering the energy barrier at the P dot PSS perovskite interface. So from here we can see the blue line, which actually is a P dot PSS TM, which is a dopant modification, and red line is a P dot PSS SM, which is a solvent modification, and the black line actually is a P dot PSS PR, which is a pristine perovskite. So we can see here the current density for dopant modification is higher compared to as solvent modification and pristine perovskite. Figure 17. The same images of the perovskite film deposited on the A, which is a P dot PSS PR. For this image, B P dot PSS SM, which is a solvent modification, and this is a second images represented with a P dot PSS SM, and C P dot PSS DM, and this is the image by P dot PSS DM, which is a dopant modification. The perovskite film formed on the P dot PSS PR layer shows strongly modulated structure with many pinholes. As we can see here, this is the black dot with many pinholes, which is exit in this image. The perovskite film form a moderately modulated structure with a full surface coverage on the P dot PSS SM layer. So this is a image with a P dot PSS SM. And the third one, the P dot PSS DM demonstrated a dense and uniform morphology, which result in a better crystallization. So for the image, we show a better crystallization compared to image A and B. And figure 18, the photoluminescence PL spectral perovskite film deposited on the three different P dot PSS HTLs. The pro surface coverage attributed to the reduction of the surface the defects of the perovskite film. Photoluminescence intensity of the perovskite film on the P dot PSS DM exhibited a higher compared with a P dot PSS SM and P dot PSS PR. As we can see from this graph, the blue line, the P dot PSS DM, which has a higher PR intensity compared to P dot PSS SM and P dot PSS PR. Addition PSS NA to P dot PSS solution leads to a highly PSS enriched top surface and forms an insulation and prevents excitant quenching. The luminescence quenching reduced in the perovskite film deposited on the P dot PSS DM layer and resulting in a largely enhanced the PL intensity. Overall comparison. The both external contour efficiency EQE and brightness luminance perovskite LEDs were improved by additional additive agent to the pristine perovskite LEDs. Figure 19 exhibits EQE improved by adding different additive agent on PLEDs. So this is a figure 19, which we have a EQE for PLED with a ETPTA for A for this figure, and then with a calcium lead iodide for this figure 19B, and C with a solvent and dopant modification which for this figure. And figure 19A show EQE reached 22.49% by adding ETPTA on PLEDs. The figure 19B shows EQE reached 6.95% by adding calcium lead iodide on PLEDs. Figure 19C shows EQE reached 5.91% by deposited P-dot PSS DM, which is a P-dot PSS layer cast from the dopant modified solution on PELEDs film. Additive agent plays a vital role in reducing non-relative recombination, enhance the hole injection, reducing contact barrier, and improve both EQE and brightness. Overall conclusion. Journal 1, Perovskite light emitting diode with external quantum efficiency 22% via small hole passivation. The conclusion: the defect passivation by employing a novel organic passivation agent, which is the ETPTA, with a C and O chemical bond function group to the intervention passivation effect and to passivate and or suppress the defect at the surface, grain boundaries, and interface of perovskite light emitting diodes. Due to the C and O chemical bond functional group interaction with under coordinated lead ions, consequently green perovskite LEDs with a ETPTA treatment reach a maximum of external quantum efficiency with an EQE of 22.49% at a 0.13 mA per centimeter square with a luminance of 77 candela per meter square. For journal 2, efficient and bright white light emitting diode based on single layer heterophase halide perovskite. The superior charge transport in the alpha calcium lead iodide and the broad white emission from self-trapped excitons in delta calcium lead iodide. Charge injection and transport are dominated by alpha calcium lead iodide and subsequently transferred to the delta calcium lead iodide. For highly improved white electroluminance, synergistic effect at the alpha to delta heterophase interface realize charge injection balance in the two phases and endow the perovskite white LEDs with a highly efficiency and brightness with a luminance with 12,000 candela per meter square and external quantum efficiency EQE of 6.5%. For journal 3, improved performance of flexible perovskite light emitting diode with modified P-dot PSS hole transport layer. Solvent or dopant modification of the pristine P-dot PSS solution to improve surface morphology and crystallization of perovskite films. P-dot PSS modification promoted to the hole injection by reducing contact barrier at HTL to perovskite interface. P-dot PSS DM, which is a P-dot PSS layer cast from the dopant modified solution layer deposited on perovskite films, show a better crystallinity and reduced luminescence and quenching. Consequently, P-dot PSS DM layer exhibited a maximum of 3,940 candela per meter square and a maximum external quantum efficiency of 5.91%. So this is a conclusion for or 3 donors. Summary: identify one preferred journal out of 3 and justify its uniqueness or novelty of work. For my summary, Journal 1 with the title Perovskite Light Emitting Diode External Control Efficiency 22% via small molecule passivation is selected for preferred journal due to it reach a maximum external control efficiency of 22%. The defect passivation method by employing a passivation agent, which is a ETPTA with a chemical bond CNO functional group to interdivision and to passivate and or suppress the surface defects, grain boundary and interface of perovskite light emitting diodes. Passivation effect on improving perovskite LEDs device performance and hence improve EQE. ETPTA layer cover perovskite LEDs firm surface with intimate contact and permit into perovskite layer and inserted between the perovskite layer and TPPI layer. Appendix. This is a appendix sample for research activity for green and electronic diamond based device. Thank you and have a good day.